That's the point.
There is no way they can miss this talk, so I'm sure everybody will join in the next minute or so. It's actually time.
Yeah, I'll check with sir again. Just want to make sure, am I audible properly here?
Yeah.
Professor Bal Krishnan may be having some internet issue. Otherwise, I'm sure he would have joined by now.
Is he joining from home or office? No idea, right?
I don't know.
I think from the home. So
Must be from
normally,
home.
yeah, must be from home, because normally for most of the talks he is joining from the home. He is not coming to the office.
His number is coming. His phone is coming busy. Maybe he's connecting through internet from phone.
Yeah.
I think Ritesh, we will leave his phone alone so that in case he wants to call, he will have it free.
Yes, sir.
So-
I'm not
so-
calling sir anymore.
Yeah, so let's not engage his line because I'm sure he's trying to join.
I will just WhatsApp him. I have WhatsApp
Yeah.
them.
Okay.
Hello, sir. Hello.
Sir, who is a chief guest for the convocation this time?
B. Santana.
Oh, B. Sandam. Okay.
St. Gobain.
Saint Gobain, I know. Great.
MD. Yeah.
Wonderful, sir.
So we're doing it in hybrid. So
Okay.
whoever can come physically will have a physical.
Right.
So far, about 150 of them express interest in coming physically.
Yeah. So if I remember correct, I was his demonstrator long time back in St. John's College.
Is it?
When I started my career, yes. Once he mentioned to me when he was a president of the Pan IIT.
Yeah.
I was education lead. At that time, we had a few interactions. At that time, he mentioned once, I don't know seriously, but I think he mentioned once.
He's now become the chairman and managing director of St. Gobain India and the CEO of Asia Pacific.
But it still stays in Chennai, sir.
Yeah. He's still operating.
sorry everyone. He's just trying to connect. I'm sending
Okay.
the link again. I hope
Yeah,
he
yeah.
will start it in a minute or so.
You cannot get to hear Professor Bal Krishnan so easily.
Yeah, in the meantime, the number of participants at this meeting is growing.
Good.
So I presume most of the students have joined by now.
Yeah. When is the inauguration of our labs? We are planning for something, right?
Physics labs.
Physics labs are new ones they have established. They wanted some formal inauguration. I don't know.
Yeah.
Professor Ramchandra Rao, somebody we wanted to invite.
Hmm.
I see some ISER faculty also has joined. I see Dilip in the list of participants.
Oh, it's good.
Abhishek Kulkarni has joined.
I think Sunil also joined.
Sunil has joined, right?
Yeah.
So
Professor Balki, where was he before he joined IIT Madras?
he was at IG Car.
Ajikar, right? That's what I recall.
Yes, yeah. He was at IG Car for a few years just before
Yeah.
joining IIT. Prior to that, he
Both-
spent a little. Yeah,
Both he and his wife were at Ajikar.
I think so.
She continued to be Ajikar.
Yeah. And then she was at Math Science subsequently. They also had a little bit of stint at TIFR
Hmm.
after returning from the US.
Finally, sir. Hello,
Yes.
sir.
Hello, sir.
Hello.
Uh-huh.
Hello. Thank you. Thank you. This,
Good evening,
Thank you for
Professor
joining, sir.
Balakrishnan.
I'm very happy to see
Hello,
you.
Pranav. Nice to see you.
Yes, indeed.
Good to see you.
What a pleasure
Hello,
it
sir.
is.
Good evening, sir.
Good evening. I think I've wasted a large number of man hours now.
No, we are all ears.
No problem, sir.
Okay, sorry about that.
Yeah.
I actually changed the computer because I have a new computer. This old one is what I'm working on now. And the new one I checked out this morning with the help of a colleague that the Zoom works, everything works. And now it says you're not authorized to be, you haven't downloaded Zoom. So I changed the computer. I came back to the old one. The connection is tenuous, but I hope it works.
Good.
Okay. Thank you, sir. Good evening, all. Today we are organizing an event inviting the freshers who joined recently for the M.Sc program. This is the second batch. So welcome all to this freshers welcoming program. Now I request our HOD, Dr. Ritesh, to deliver a welcome speech.
Good evening, everyone. I'll just take a minute to brief about the department, and I would very happy to see Professor Bal Krishnan to be agreed for doing this talk. Physics department is currently having 7 faculty members, regular faculty members, and 2 of the senior professors we all know, Professor Deshmukh and Professor Natarajan from IIT Madras, are also with us. And currently the department is very balanced between theoretical and experimental research. We almost have equal number of faculties working in theoretical area as well as experimental area. Major thrust area, currently we are focusing on quantum computing, quantum information technology, science and technology. We are also focusing mainly the AMO related science and technology, ultra fast science. Then we have colleagues from condensed matter physics department side, who's both sides. We have theoretical as well as experimental aspects in condensed matter physics, working on various materials, mainly in line with the thrust areas of IIT Tirupati. This is our second batch of M.Sc. We have started our M.Sc academic program last year with a capacity of 15 students. This year, 14 new students has joined this program. So currently we have a M.Sc strength about 29 students. We also have PhD students, around 15 PhD students are working in the department with other faculty members. Few more faculty members may join soon, so department is expected to be bigger in the near future. And we have also established PG labs, PG lab 1, 2, and advanced PG lab, which is currently under progress. We have established UG lab long before at the starting of the IIT Tirupati. In fact, that time I didn't join. Professor Natarajan was the key resource person in developing that lab. We have always received a good motivation, support from our senior members and also from higher authorities, Professor Satyanarayana, Director IIT Tirupati, and all others always motivate us, support us in this. And with this, I welcome all the students and I request our Director, Sir, Professor Satyanarayana, to please make some address remark to the audience.
Thank you, Ritesh. First of all, I would like to thank Professor Bal Krishnan for accepting this invitation. In fact, I was trying to get him, I think last year, the year before that, as the chief guest for the Teachers' Day, and he was not available at that time. And it so happens that today is the day after Teachers' Day, so that way, you know, he is at IIT Madras. We used to consider him as the personification of the teacher to be emulated, and I think our students are very fortunate to have the opportunity to listen to him. You know, his classes were extremely popular. His NPTEL, the amount of time he spent on preparing these NPTEL courses, you know, at IIT Madras, which are once again very popular, with one of the most viewed courses. So So I still, Professor Bal Krishnan, I'm still hoping that sometime I can get you to come and physically visit our institute. I've known him since I joined IIT Madras. So the physics department at IIT Madras, we started off in 2015, and we were fortunate to have the mentorship of both Professor Natarajan and Professor Deshmukh. And as soon as he retired, Professor Natarajan had just retired, and we managed to get him re-employed. And then Professor Deshmukh, he had not yet retired, but he came and taught here in the first year, and immediately after his retirement moved here. So both their guidance and mentorship helped lay the foundation of our physics program here. And they had Professor Natarajan, him with hands-on person with setting up labs and motivating young kids into science. And Professor Deshmukh, with his contacts in the AMO area, brought in a number of people to come and visit us, whether it's from TIFR and NPL or from US and other countries. Also put together this team between IIT Tirupati and IISER Tirupati. That's another thing that we are very fortunate to have an IISER co-located with us. Their campus is on the same road, 3 kilometers away from us. And we are doing a lot of things together. I'm very happy to see a few IISER colleagues also in the session today. We're doing so. We found that based on these interactions with the experts coming in, saying that you have a pretty large young group of people in this area of atomic, molecular, and optical science technologies. So Professor K. Ganesh, the director of IISER, and me then said, okay, with Professor Deshmukh's guidance and other things, we started the Center for Atomic, Molecular, and Optical Science and Technology between the two institutes. That's been quite very active. In fact, they did their anniversary program recently. And then the other area where we have a strong presence is in the area of condensed matter physics. We have colleagues working in that particular area. And recently we did and hired about 5 faculty members, out of which the first Arvinda has joined us. And 4 more are due to join very soon. All of them are theoretical people in various areas of physics, high energy physics, and so on. So IIT Tirupati is, growing reasonably well. We have 100 plus faculty members right now in our institute full time, and we have given enough thrust to, not only engineering but also to the sciences. I just went up to the chemistry lab and came down. So, first year was a washout for all of them from a lab experience point of view. They had to take all classes online. So we have brought the second year students back so that we can start the labs. So similarly, Professor C.P. Rao, who was from earlier at IIT Bombay, who's here mentoring the chemistry, took me up to show that the lab classes are going on, action is back. People are back in action with their hands.
We are not.
Oh, you're able to hear me?
Yeah, now,
Yes,
sir.
yes.
Now it's
In between, just a minute ago, it was.
Oh, I'm sorry about that. So we're very glad. So I would like to join my colleagues in welcoming the new batch of students who have joined the M.Sc program. We started with the M.Sc programs in mathematics 2 years back. The third batch of mathematics and statistics joined this year, and physics and chemistry we started last year. So this is second batch. Also welcome the first batch also on campus. Have all of them come, Ratish, to campus?
11, 12 actually have arrived. 12 or 13. 13
12 or 13 out of 14 have come. So I would like to welcome them to the campus. I was very worried that they will get correspondence course degrees out of IIT Tirupati with all online teaching. So I'm glad we could get them to campus. And let me not stand between Professor Bal Krishnan and the students and the other people in listening to what he has to say. Thank you very much, Professor Bal Krishnan, for accepting our invitation.
Thank you, sir.
Thank you, sir. Thanks for giving a very nice talk. Now I invite Professor P.C. Deshmukh to introduce our speaker, Professor Bal Krishnan.
Thank you. Thank you very much, Arvind. And thanks to Ritesh and everybody at the Department of Physics there. Professor Satyanarayana has already shared his experience of being at IIT Madras, and he mentioned what a popular teacher and educator Professor Bal Krishnan is, and it is a great moment for all of us. I mean, I'm sorry, I am reminded of something I have learned as a child in Marathi. They say sadhu santa yeti ghara tochi diwali dasara. What it means is that when some great person visits your home, that is the day to celebrate Deepavali and Dasara and festivals of this kind. And means the reverence we have for Professor Balakrishnan means he is a teacher to millions. He has millions of students across the world, and he really doesn't need much introduction as such, except that some of the younger students may not know about some of his background. So I will mention it very briefly. Professor Balakrishnan did his Bachelor of Science and Master of Science at the University of Delhi. And then he did a PhD in theoretical high energy physics from the Brandeis University in 1970. And subsequently, he spent some time at TIFR and also at IG CAR at Kalpakam before he joined IIT Madras as a professor in 1980. And that reminds me, because this is also combined with a welcome event for our M.Sc students. So let me share a personal note with them that I was actually personally an M.Sc student when I first heard Professor Bal Krishnan. He had returned from the US. He was, I believe at the time, at TFR, and I had an opportunity to listen to one of his talks, and Radha also spoke on that occasion, and we heard both Professor Bal Krishnan and Professor Radha Balakrishnan. And there is a similar moment now that all our young M.Sc students have, and what an impression it left. It left a lifetime of an impression, because what a speaker he is. And at IIT Madras, he has taught courses in all branches, practically all branches of physics, undergraduate courses, advanced courses for students in doing M.Sc, PhD courses. And he's being a very complete physicist. He has taught almost every topic in physics. And his special interests have been in particle physics, many body theory, stochastic processes, random walks, condensed matter physics, nonlinear dynamics, chaos, quantum dynamics, and you name it, and he has actively contributed to the field in a number of research areas, publishing papers in premier journals, written articles, and several books. Beyond the Crystalline State, for example, which is perhaps one of his earliest publications as a book. And then he wrote on non-equilibrium statistical mechanics. He has 2 recent books on mathematical physics. And, means he has taught through every medium, the classroom instruction, the NPTEL courses, you name it. He has got like 7 NPTEL courses, and millions of viewers and many millions of appreciations. So he's a great teacher. He's of course a fellow of the Indian Academy of Sciences. He's currently very active in research in quantum dynamics as a adjunct professor at IIT Madras. He works on random walks on fractals, recurrent statistics in coarse-grained dynamical systems. And today, he is talking on a very fundamental problem, which everybody is familiar with. Right from the high school, we know about the Kepler-Newton problem, and it has got very special features. And who better than Professor Bal Krishnan to tell us about it? Welcome to you, Professor Bal Krishnan.
Thank you.
Very hearty welcome to you. Yes. Please, Professor Bal Krishnan.
Thank you. Thank you, Professor Deshmukh, for that extremely generous introduction. You'll pardon me if I say that I could hardly recognize myself. It was most generous and very kind of you. Professor Satyanarayana, thank you very much for this kind invitation. Professor Deshmukh, Professor Ritesh, and your colleagues, Dr. Aravinda and other colleagues. I'm very happy to be here this evening, at least virtually, on the day after Teachers' Day. I have to tell you that I belong to a generation which was born before independence. And I make a special mention of this because yesterday I had been to IIT, the day before yesterday, to get a tag on my car so that I could pass through their security. And the security person in charge, when he was filling out my particulars, spontaneously exclaimed, he said, "You're born before independence." And it occurred to me that this is an event which most people in India today, since I belong to the small minority of people over 75 on the wrong side of 75, most people have no clue at all as to what India was like before independence. Of course, I refrained from pointing out or suggesting to him that it might have been cause and effect, my arrival and independence, but I thought that's a joke which he might not appreciate. So I refrained. What I would like to talk about today, as Professor Deshmukh mentioned, is the classic problem which set off all of physics itself, in a sense. So let me start screen sharing and get down to business. I don't think I'll be able to, since I myself wasted a lot of time in the beginning trying to join the meeting with several fits and starts. I shall penalize myself by not giving the second part of my talk, but I'll stick to the first part. And if I manage to complete that, it already have served a good purpose. It's going to be a rather technical talk, but I'll try to explain things as clearly as possible and as slowly as possible. So let me start screen sharing, and I need possibly some help in this. Is my projection visible? Is this visible?
Yes, sir.
Yes, sir. Yes, sir.
I need a bit of a cue here.
That's fine, sir.
Yeah, it is
fine?
good.
Let me
It
just
is
check.
good. Yeah, it's good.
I just need to check that it scrolls, which is always a pain. I'm not able to scroll it for some reason. Are the slides changing?
Not yet.
Not yet.
I see.
We are only on the title slide.
For some reason, it's just slow.
Okay. Are you using a mouse?
So,
or?
I'm using a mouse.
Right.
Yes.
Yeah.
Yes.
Now it's changing, sir.
It's scrolling.
Now it's changing. Okay.
Yeah.
So I hope it's legible. I hope it's large enough. I've got it on full screen here. I hope that helps.
Yeah, it's good.
So I'm going to speak about this central force problem, but not in 3 space dimensions, but in an arbitrary number n of dimensions, like 2, 3, 4, any number you like. And let's see what this problem gets us and where it gets us. So here's a brief outline of the talk. I'll start with a very brief introduction. I'll do a quick recap of Hamiltonian dynamics, and then go to the main talk, the topic that I'd like to emphasize today, which is what orbital angular momentum looks like in n dimensions as opposed to 3 dimensions. And that will tell us, take us on to the integrability of the n-dimensional central force problem. And if time permits, I will come to these interesting topics, such as dynamical symmetry of the n-dimensional Kepler problem, the unitary symmetry of the isotropic oscillator, and conclude with a few brief remarks. I'll almost certainly not have time to do the last 2, dynamical symmetry and unitary symmetry, but let's see how this goes. As I've said before, the very genesis of modern physics is in classical mechanics. It started with Newton's laws of motion, and if you remember your history, Newton's laws of motion were actually motivated by Newton's objective of deriving Kepler's laws of planetary motion. Now, the problem of a particle moving in an inverse square force field, and more generally in a central force, has ever since served as a model in all subsequent developments, both in classical mechanics and in quantum mechanics. In the modern context, our emphasis is not so much on the original motive of solving differential equations to get trajectories of particles, but rather the focus is on notions such as symmetry and invariance and conservation principles, integrability, and so on. A very basic theme in modern physics is the following. Very interesting feature is to embed a given problem in a general family of similar problems for a better perspective on the entire issue. For instance, the famous dependence of critical exponents in condensed phases of matter on the dimensionality of space, space groups in n greater than 3 dimensions, quantum field theory in d+1 dimensional space-time, and so on, are all efforts in this direction, namely to embed a given problem in a given space-time dimensions in a family of general space-time dimensional problems. So in this spirit is what we're going to use for the central force problem in n dimensions. And most of what I'm going to say appeared in an article in Resonance last year in 2020. I believe it was the April issue of Resonance. This generalization yields useful insight and a better perspective on various aspects of the problem. And it's proved to be a very powerful tool in the analysis in problems, particularly in quantum field theory, where there's this a technique called dimensional regularization, which is a very powerful one. Now, here's a very brief recap of Hamiltonian dynamics. We start with n degrees of freedom, described by generalized coordinates q1 to qn, with conjugate momenta p1 to pn, and I'll collectively denote these by q and p. And you're given a Hamiltonian function h of q and p. The dynamics is then given by 2n equations of motion. The dot denotes a time derivative, and the time derivative of each coordinate, if you like the generalized velocity, is the partial derivative of the Hamiltonian with respect to the conjugate momentum. But the time derivative of the corresponding momentum is minus the partial derivative of the Hamiltonian with respect to the corresponding coordinate here. This minus sign is absolutely crucial and is in fact the basis of all the symplectic structure and other interesting mathematical structures that Hamiltonian dynamics displays. Now, these equations are a kind of generalization of Newton's equations of motion, if you like. And these 2n partial differential equations have to be solved in order to find the trajectory of the particle in phase space, in the q and p space at any given time, given a set of initial conditions. What's interesting is that unlike Newton's equation of motion, these equations are first order in time, and therefore there's a unique solution as a function of time for each set of initial conditions, q0 and p0. And this traces a trajectory in the 2n dimensional phase space here. So this is basically a very quick recap of Hamiltonian dynamics, but there's more to it, and that's the following. In practice, these equations of motion are coupled equations, almost always nonlinear and almost always not solvable, in the sense that they're not integrable in closed form. They can always be solved numerically on a computer. Once you give me a sufficiently small time step, I can trace a trajectory, but they're not generally analytically integrable. And also, it's very difficult to eliminate some of the unknowns to obtain higher order differential equations for the rest of the variables. They're almost never fully integrable to yield the trajectory as explicit functions of t. In other words, there's always dynamical chaos, almost always, with a few exceptions. But the exceptions turn out to be extremely interesting exceptions, and we're going to focus on one of them today. For any given Hamiltonian, the extent of integrability, how far you can go in integrating these 2n equations, is a very primary concept concern in Hamiltonian dynamics. Okay. One more background piece of information. For any two functions of the phase space variables, one defines something called a Poisson bracket between two functions, which is just this combination of partial derivatives with respect to the q's and p's here. This is like the commutator in quantum mechanics. It plays an analogous role here. And in fact, it was Dirac's inspiration for postulating quantum mechanics, formulating quantum mechanics the way he did. Now we have what are called canonical Poisson brackets. The coordinates Poisson commute with each other are an involution with each other. The momenta are also in involution with each other, which means the Poisson brackets are 0. But a coordinate with its corresponding momentum, the Poisson bracket is unity on the right-hand side. The Kronecker delta tells you it's 1 for I equal to j. And these Poisson brackets have a set of algebraic properties: antisymmetry, linearity, bilinearity in this form, the chain rule, of course, like the Leibniz chain rule in calculus for differentiating a product of functions, and then something called the Jacobi identity, which is extremely crucial in ensuring that functions of Q and P form what's called a Lie algebra under the Poisson bracket operation. So this is the mathematical structure that underlies Hamiltonian dynamics. Now, we're not going to get into the mathematical structure, but we're going to do something very physical, and that's the constant notion of constants of the motion. So if you take an arbitrary function of all the Q's and P's, it remains unchanged in time at its initial value if its total derivative with respect to time is 0. Using the equations of motion, this condition becomes the condition that this function f Poisson commutes or is in involution with the Hamiltonian. If that happens, then it's a constant of the motion. If it doesn't happen, it's not a constant of the motion. Now, what's the significance of a constant of motion? Very significant, it turns out. If f1 of qp is a constant of the motion, every phase trajectory lies on some level surface on which f1 of qp is constant in a 2n dimensional phase space. But in 2n dimensional phase space, once you put a scalar condition like f1 of qp equal to constant, you are left with a 2n minus 1 dimensional hypersurface. If you have two constants of the motion which are independent of each other, functionally independent, I call them phi coms, then the phase trajectory lies on the mutual intersection of these two constants of the motion, which is on a 2n minus 2 dimensional intersection of the two level sets. And the intersection of three phi com level sets is of dimensionality 2n minus 3 and so on. And eventually you want a one-dimensional phase trajectory. So in principle, the trajectory will be completely determined if you can find or identify 2n minus 1 functionally independent constants of the motion. It's also very clear that in 2n dimensional phase space, the maximum possible number of phi coms is in fact 2n minus 1. If you had 2n, the mutual intersection of all these would typically be a point and not a trajectory in phase space, and there would be no motion at all. If you had less than 2n minus 1, the system is not fully integrable or maximally super integrable, as the technical term goes. So this is for explicitly time independent phi coms. There's a small extension for time dependent phi coms, which we won't get into here. A very important notion in Hamiltonian mechanics is what are called canonical transformations. The identification of more and more phi coms very clearly brings us closer to a complete solution of the equations of motion. This process is aided by the so-called canonical transformations, which are nothing but invertible changes of variables from small q, small p to capital Q, p, which are functions of the little variables, such that all the canonical Poisson brackets are preserved and the volume element in phase space is preserved. Which implies, and this can be shown fairly easily, that these conditions imply that Hamilton's equations of motion remain Hamiltonian in structure. So if the old Hamiltonian is h of little q, little p, and that transforms to a capital K of qp, the new Hamiltonian in the new variables, then you're guaranteed that q dot is delta k over delta p, and p dot is minus delta k by delta q. Now you might ask, what's the advantage of changing variables if it looks exactly like the old equations of motion? The answer lies in the fact that you might be able to find n constants of the motion in involution with each other. And then there's a theorem says, Liable Arnold theorem, it says that they're guaranteed to exist a canonical transformation to new variables. Instead of capital Q and capital P, the conventional notation is theta and I, called angle action variables, such that the transformed Hamiltonian depends only on the action variables I and not on any of the angle variables theta. In other words, if this magic happens, then the new Hamiltonian depends only on n phase space variables and not 2n of them. And immediately the equation can be integrated. You can test functional independence by looking at the rank of the Jacobian matrix, but we won't get into that at this point. So the complete integrability follows, and this is a technical piece of information which I've written here for completeness, but I'm not going to use that very much. It's just a matter of little verification to see that once you have these action angle variables possible, then the system is completely integrated. All the equations of motion can be solved in closed form, and you can write down the explicit solution. There's a little catch, not a very little one, but there is a catch. And the catch is this Liable-Arnold criterion for integrability says absolutely nothing about how one is going to go about finding the phi coms in involution. How are they going to be done? How is this going to be done? There's no clue from this criterion at all. For that, you have to actually look at special cases and do it based on experience and perturbations and so on and so forth. What's interesting is that if there exists less than n phi coms in involution, the Hamiltonian is non-integrable. There's definitely chaotic behavior for at least some initial conditions. Maximally chaotic if there's no phi com at all except the Hamiltonian itself. That's in fact the generic situation. On the other hand, in the other direction, it's not possible to have greater than n phi coms in involution. One might have greater than n phi coms, but they will not all be in involution with each other. And what's needed is exactly n phi coms in involution as a necessary and sufficient condition for integrability. Greater than n phi coms, not all in involution, is what is called super integrability due to some kind of hidden symmetry, hidden or overt symmetry in the Hamiltonian. And if you have 2n minus 1 phi coms, that's the maximum number possible, you have what's called maximal super integrability, generally due to some dynamical symmetry. So what I want you to bear in mind are these numbers: n degrees of freedom, 2n dimensional phase space, n phi coms in involution means integrable, greater than n phi coms, not all in involution, means super integrability, and 2n minus 1 phi coms implies maximal super integrability in a very symmetric situation. Well, there's a very deep mathematical structure underlying Hamiltonian dynamics called symplectic geometry. The phase space of any Hamiltonian system is what's called a symplectic manifold with a certain natural metric and so on. We will not get into this here, but I want to mention that modern classical mechanics is actually an active field of research. I make a special point of this. It's a field of research in both physics and mathematics, because it's now been subsumed into the broader framework of nonlinear dynamics, ergodic theory, and dynamical systems. I say this especially to students because there's this impression, of course, that old means obsolete and new means profound. Nothing could be further from the truth. There's always stuff to go deeper and deeper in, and the connections between mathematical structures and classical dynamics is still a very active field of research, as is the connection between classical dynamics and quantum dynamics, for instance. So these fields are all alive, and a lot of development has taken place, and they all have research level problems of great interest. Now for the central force problem, which is what we're going to talk about. A particle of mass m moves in n-dimensional space. Cartesian coordinates run from x1 to xn. Conjugate linear momentum components run from p1 to pn. The canonical Poisson brackets are x with x is 0, p with p is 0, x with p is a Kronecker delta. The Hamiltonian is a function of the coordinates and the momenta. It's given by kinetic energy term p squared over 2m plus a potential which depends only on the radial distance from the origin here. So it's a spherically symmetric potential that we're talking about, leading to a central force. Because as you can see, the force on the particle is given by minus the gradient of the potential. And since that depends only on r, the force is directed either towards or away from the origin of coordinates. And the equations of motion can be written down, the Hamilton equations. Here. For instance, a central force in 2 dimensions. This is completely trivial. You have a Hamiltonian, which is a constant of the motion, an orbital angular momentum L, which is x1 p2 minus x2 p1, which are 2 phi coms in involution with each other. It's easy to show that the mutual Poisson bracket is 0, and this is the constant of the motion, the orbital angular momentum. H with L is 0. Since n is 2, and you have 2 such functions in involution with each other, H is integrable. So the Liable-Arnold criterion is completely satisfied. You have 2 phi coms in 4-dimensional phase space, so the problem is reduced to quadratures. For any given E, the value of the Hamiltonian and L, the value of the orbital angular momentum, you have to solve the first order ordinary differential equation for the radial coordinate, which is m over 2 dr by dt squared plus L squared over 2m r squared. That's twice the moment of inertia plus the potential is equal to E. If you have one more phi com, if any, it will make H maximally superintegrable because you would have 3 phi coms in a 4-dimensional phase space. So this problem in 2 dimensions is reduced to quadratures and we take it as done. That's it. In principle, it's done. In 3 dimensions, slightly more complicated situation, you now have an angular momentum that's a vector. So if you denote by Lij xi pj minus xj pi, the orbital angular momentum is a vector comprising 3 components, L1, L2, L3, which are actually L23, L31, and L12. I'm substituting to the indices values here. H and L together give 4 phi coms. The phase space is 6-dimensional because you've got 3 coordinates and 3 momenta, and you've got between Hamiltonian and the orbital angular momentum, you have 4 phi coms. But the problem is they are not in involution with each other, all of them, because Li commutator or Poisson bracket with Lj is epsilon ijk Lk. L1 with L2 is L3 and so on, cyclic commutation. Hence, the sets of constants of the motion in involution can only include one component of L, any one of them, any L dot n. As is well known, the total square of the total angular momentum is also in involution with all the components of the angular momentum as well as the Hamiltonian. So we can actually choose the Hamiltonian, the square of the orbital angular momentum, and any one component, which could be taken to be the third component, for instance, are in involution with each other in a 3-dimensional phase space, and therefore the Hamiltonian is integrable in this problem. Just as in the 2-dimensional case, the problem is integrable here too. What's interesting is that the angular momentum plays a very, very fundamental role in this. It gives you exactly the number of phi coms along with the Hamiltonian to make the Hamiltonian integrable. But now you can go back and say the Hamiltonian, L1, L2, and L3 are 4 phi coms in 6-dimensional phase space. So H is also superintegrable because of angular momentum conservation. So once again, the problem is reduced to quadratures for E and L squared, and you have to solve a first-order differential equation for the problem to be completely solved. One more phi com, if any, will make H maximally superintegrable, and that doesn't always happen. So to sum up, in both 2-dimensional and 3-dimensional space, the very fact that the Hamiltonian is rotationally invariant in a central force, the rotational invariant of the Hamiltonian automatically implies that the central force problem is not only integrable, it is also superintegrable and falls just 1 phi com short of maximal superintegrability. So that's a very powerful statement, a general lesson from 2 and 3 dimensions. What happens in n greater than 3 dimensions? Something very, very interesting happens now. As before, the rotational invariance of the Hamiltonian in n-dimensional space implies the conservation of angular momentum, which is now a rank 2 tensor. Lij is xi pj minus xj pi, an antisymmetric tensor of rank 2 with n choose 2 equal to n times n minus 1 over 2 components. But you see, now we run into a difficulty. If you look at what NC2 is, it's going like a quadratic function of n for large values of n. If you're in 60 dimensions, for example, this is of order 60 squared essentially. But NC2 goes like n squared over 2 for very large n, and is already greater than even the phase space dimensionality as soon as n is greater than equal to 6. So what's the conclusion? It's obviously impossible that these are all independent functions. So it's clear that all components of Lij cannot be independent constants of the motion. There must be relations among them. And the 2 crucial questions arise immediately. First, how many of these Lij are actually in involution with each other? Namely, their mutual Poisson brackets are 0. And how many of the Lij are functionally independent constants of the motion? So 2 problems which are different from each other. The first is to find out how many have got Poisson brackets which vanish. And the second is how many of them are actually functionally independent phi coms so that you can they help towards integrability. So these are the 2 questions we're going to spend some time answering. First, we want to find out how many of the Lij's are in involution with each other. For that, you first need to know the angular momentum algebra in n dimensions. And it turns out that the Poisson bracket of Lij with LKL is this string of things which are proportional to the L's here, which implies, because of the canonical deltas, that if Ij, K, and L are distinct indices, like in 4 dimensions, they are say 1, 2, 3, 4, or any permutation of 1, 2, 3, 4, then the Poisson bracket vanishes. So if Ij, K, L are distinct indices, the Poisson bracket vanishes. Now, for even values of the dimensionality, and here's where it starts differentiating between even and odd spatial dimensionality, let me say in general, as a general remark, that spaces of even and odd dimensions, respectively, are very different from each other. The rotation group in an even number of dimensions is very different from the rotation group in an odd number of dimensions. Many other distinctions of this kind occur. So one has to be careful about the dimensionality's parity, whether it's an even or an odd number. For an even dimension, let me call it 2 nu, n is equal to 2 nu, we can choose as the set of angular momentum components in involution with each other n over 2 components, and that's very easily done. Just choose L12, L34, L56, etc. up to L2 and 2 nu minus 1, 2 nu. They're all independent of each other. They involve different coordinates and momenta. It's not a unique choice, but the number of elements n over 2 is unique. So the first question is answered. How many of them are in involution with each other? The answer is n over 2. This is also called the rank of the rotation group in 2 new dimensions here. And it comprises what's called the Cartan subalgebra of the Lie algebra of the special orthogonal group in 2 new dimensions. Okay. So that's worth keeping in mind. What happens in odd dimensionality spaces? Well, if n is 2 nu plus 1, we can choose as the set in involution. You can start by saying, I'll choose L12, L34, L56, L2 nu minus 1 up to 2 nu. Or I could skip 1 on this side and choose L23, L45, and so on till L2 nu, 2 nu plus 1. Just as I left out L with 2 nu plus 1 here as the index, I leave out 1 as the index here, and I can choose either of these. And the second is more convenient for our purposes. And this also is a number is unique. Each of these sets has n minus 1 over 2 components. So the rank of the Lie algebra SO2 nu plus 1 is also nu, exactly like that of SO2 nu. So the special orthogonal group in 2 new dimensions has a rank nu, n over 2, as a rank here n minus 1 over 2, which is also nu here. In short, the rank of SON for arbitrary n is the floor function of n over 2. This is the largest integer contained in n over 2. Together with 2 with the Hamiltonian, we now have n over 2 plus 1 phi coms in involution. But we need n of them for integrability, and this is roughly of the order of half n. So we've got a long way to go. What should we do? Exactly what we did in 3 dimensions. We used L squared. So we need to now find the Casimir invariants of the algebra, which means we need functions of the Lij that are in involution with all the components of the angular momentum. And I've said functions in plural because, as you can suspect, we may have more than one Casimir invariant. There's a simple result. There's a result in semi-simple Lie algebras. I won't explain what semi-simple is. The number of Casimir invariants is equal to the rank of the algebra, which is also equal to the number of components of the elements of the algebra which commute with each other. So the Casimir invariants are homogeneous symmetric polynomials in the angular momentum components. For even n, once again, these are new polynomials of orders 2, 4, etc. up to 2 nu minus 1, twice nu minus 1, and nu. For odd, there are 2 new polynomials of order 2, 4 up to 2 nu. But we must still check how many of these polynomials are independent of each other after the relations between the Lij are imposed. So we need an alternative approach to count the number of Casimir invariants. Whenever you do any combinatorial problem, you must count in at least 2 different ways to make sure your answer is right. Okay. So the technique is to consider the quadratic partial sum C sub n, which is just the sum over the squares of the angular momentum components. Since I sum unrestrictedly over I and j, I put a half here, summed up to n, where n is greater than or equal to 2. It's straightforward to show that these are all Casimir operators. They commute with all the Poisson brackets, provided certain with all the Lij's, provided certain conditions are satisfied on this n. So either n is bigger than both k and l, or n is less than both k and l, roughly speaking. And then in that case, this Poisson bracket is 0. But if n is between k and l, it's not equal to 0. And the sums of Cn for specific values of n give the rest of the 5 comps in involution. This was proved many years ago by several people. A very interesting place where I found a good proof is a paper by Gallup in the Journal of Molecular Spectroscopy way back in 1959. Even in odd n cases differ slightly as might be expected. So let's do the counting now of the number of quantities, constants of the motion that we have in, for this problem to see whether it's integrable or not. We need to count the number of constants of the motion in involution. The new constants of the motion C2, C4 up to C2 nu are the following. They are independent of each other and they are in involution with each other and with the components of the angular momentum already enumerated. So here is the list for even spaces. The Hamiltonian is a constant of the motion. Commuting with the Hamiltonian and mutually commuting with each other are the angular momentum components L12, L34, etc. New of them. And then these Casimir, quadratic Casimir operators or operators which commute with all the angular momentum components and with each other. There are nu minus 1 of them. So you add up 1 plus nu minus 1 and you end up with 2 nu equal to the phase space, the dimensionality of the coordinate space, and H is integrable for even n. So this proves rigorously that the central force problem in even number of dimensions is actually integrable. What does one do for odd dimensions? Well, the 5 comps now are the Hamiltonian, these new components of the angular momentum, and these Casimir operators here. They have been chosen in such a way that their Poisson brackets with each other and with all the other components here are 0 here. And once again, you discover that you get exactly n constants of the motion in involution with each other, and H is integrable, therefore, for odd values of n as well. So the conclusion is that the central force problem is integrable in the sense of Liable-Arnold in all dimensions n greater than or equal to 2. What now remains is to determine the extent of the superintegrability of this Hamiltonian owing to angular momentum conservation. How many functionally independent constants of the motion are there? And that's an interesting question, which is again combinatorial. In general, the generators of a Lie group, such as the orthogonal group SON, are independent quantities. But we're actually dealing here with a specific tensor representation of the generators as functions of the phase space variables, Lij's xi pj minus xj pi. They must satisfy certain algebraic entities, otherwise the number of independent angular momentum components will exceed the phase space dimensionality itself, which can't happen. So what's the trick here? Well, one observes that if you define Lij in this fashion, this antisymmetric tensor, then a simple piece of algebra shows you that L13 L24 minus L14 L23 simplifies to L12 L34. Just simple algebra here. But 1, 2, 3, 4 are independent entities here, independent indices. It follows, therefore, that if I substitute 1, 2, 3, 4 by different indices I, J, K, L, then this identity is valid. And the question is, how many such independent relations are there? There are several ways of doing this. Again, a combinatorial problem. And here's the way which I like best because it's a cute way of doing it. Suppose there are mu of n independent relations of this kind here. Since NC2, that's the number of angular momentum components, minus mu n must be at best linear in n. You can't have a quadratic term there, it will exceed phase space dimensionality. Mu of n must also be a quadratic in n to cancel the quadratic dependence on n of NC2. But in 2 and 3 dimensions, there exists no identities between the angular momentum components. In 2 dimensions, you have only one component of the angular momentum. In 3 dimensions, you have Lx, Ly, Lz, and there are no relations between them. Therefore, this quadratic must be of the form constant times n minus 2 times n minus 3, because it must vanish when n is 2 or 3. And it remains to find the constant c. But in 4 dimensions, there's exactly one relation, which is written down here. And therefore, mu of 4 is 1, which gives c equal to half. And therefore, the number of independent relations between the Lij is mu of n is n minus 2 times n minus 3 over 2, which is n minus 2 choose 2. The number of functionally independent angular momentum components, Lij, finally, therefore, is the difference between these two, and that's 2n minus 3. Note that all 6 pairs of indices appear in the relation between the Lij involving 4 distinct indices. There are therefore no other such relations at all. There's an alternative argument which we can give in terms of the components directly, and I'll skip this argument here. So, including the Hamiltonian, we have 2n minus 2 phi coms for the central force problem in n dimensions, just one short of maximal super integrability. So again, we see a powerful relation has emerged here, conclusion has emerged here, that angular momentum conservation in a central force in n dimensions not only makes the Hamiltonian problem integrable, it also makes it super integrable, leaving it just one short of maximal super integrability here. And it's all from simple angular momentum conservation. So it's finally reduced to quadratures, exactly as in the earlier case here. And that immediately tells you, angular momentum conservation tells you, that the path of the particle is always confined for given initial conditions to a plane in n-dimensional configuration space. So the orbits are all planar, as we know in the 3-dimensional case here. I'm not going to give the proof here, except that I'll make a mention of the Kepler problem in 3 dimensions and show you very quickly what happens in n dimensions and skip the rest of the talk. In the Hamiltonian in 3 dimensions, the Kepler problem is with a potential which is a 1 over r potential, an attractive potential. In this case, it's well known that you have the Laplace-Runge lens vector, LRL vector, which is defined as P cross L minus MKR, kappa r over the magnitude of r. But A can only provide one more constant of the motion, which is functionally independent, because it satisfies 2 scalar conditions. You see, the phase space is 6-dimensional. You have 1 phi com in the Hamiltonian, leaving 5 dimensions, and you have 3 angular momentum components. That's 1 plus 3 equal to 4. On a 6-dimensional phase space, you can at best have 1 more phi com. That's all. So this A, although it's a vector, can only provide 1 more phi com, and it satisfies 2 scalar conditions. A is perpendicular to the angular momentum. It's in the plane of the orbit. So one component is knocked out by that condition. And the square of A depends on the Hamiltonian, the square of the angular momentum. So one more component is knocked out. So together with H, L1, L2, and L3, that adds up to 5 phi coms in 6-dimensional phase space, and H is maximally super integral. As a consequence, the phase trajectory for any energy bound curve, bound state is a simple closed curve, and we know it's an ellipse in position space and a photograph or a circle in momentum space. There's a theorem called Bertrand's theorem in 3 dimensions. The only central potentials for which all bounded orbits are closed orbits are the inverse square potential and the harmonic oscillator potential, the isotropic oscillator potential. And this statement turns out to remain true for central potentials in n dimensions. I'm not going to go through the Kepler problem in 2 dimensions, except to say quickly that there is an analog of the Laplace-Runge lens vector. It's given by this term here, which involves the antisymmetric tensor in 2 dimensions here. I state this because it's generally not mentioned at all, but it's easily generalized. In n dimensions, and that's an interesting thing, it turns out to identify the LRL vector in n dimension, we must generalize the term P cross L in the definition in 3 dimensions. Remember that the angular momentum is not a vector in more than 3 dimensions. It's in fact a tensor of rank 2. And then the LRL vector in n dimension is a constant of the motion given by this. AI is Lij Pi, contracted index I is summed over, minus Mk xi over R. The contracted index J is summed over here. So it's a function of I alone. And there are n such components, and that gives you the n-dimensional vector. And then from that, you can again show that there are relations between the components of A, which reduce the number of independent components that it can contribute to the phi coms to exactly 1. And I won't go into that here. And the Hamiltonian, the conclusion is that in n dimensions, the Hamiltonian, the angular momentum, and A, the Laplace-Runge lens vector, give 2n minus 1 phi-cons, making the Kepler problem in n dimensions maximally superintegrable. For any general central potential, you have only h and Lij, that gives you 2n minus 2, and you are one short of maximal superintegrability. The moment you have this Laplace-Runge-Lenz vector in the inverse square potential, power potential, you have one more, and it makes it maximally superintegrable. As a result, for each energy less than 0 in coordinate space, the orbit is a closed curve. In fact, it's an ellipse, as in 3 dimensions. Each trajectory in momentum space is also a simple closed curve. If the orbit lies in the x1, x2 plane initially, then it lies in that plane forever. So it's in the small 4-dimensional submanifold of the phase space here. And finally, it's readily shown that all 3 of Kepler's laws of planetary motion remain valid in the n-dimensional case because of conservation of angular momentum and the existence of the Laplace-Runge-Lenz vector. Now, why this magic? Why does this happen here? I'm not going to go into this in any detail here, except to say that if you go to action angle variables, the Hamiltonian in the new variables is purely a function of the action variables, and there are n of these. In spherical polar coordinates in n dimensions, there's a radial component, there's the first polar component angle θ1, and then there's the azimuthal angle I phi. So this is a total of n coordinates here. And the actions add up in this fashion, and the derivatives with respect to any of these are all equal to each other. And that's the reason why the motion is completely periodic and becomes completely integrable. The motion becomes very simply periodic with a single time scale, which is simply the orbital period. This is a separate topic altogether, and I don't have time to mention this here. So perhaps this is a good place to stop here, except that I'll keep this on with the punchline here, that all 3 of Kepler's laws of planetary motion remain valid even if the spatial dimensionality increases to n, where n is an arbitrary integer greater than 3, equal to 3. So with that, I'll maybe conclude here. And if there are any comments or criticisms, I'd be happy to hear. Thank you very much for your attention.
Thank you very much, sir.
Thanks, sir. Thanks for giving a wonderful talk. Now the floor is open for discussion. And if anybody has a question, please unmute yourself and you can ask directly to Professor Bal Krishnan.
You can write your question in chat box also. If you...
Yes.
I don't guarantee to be able to read the chat box.
No, sir,
No,
I
sir.
will read for
I
you.
don't know where it is.
No, sir. We will read and tell you,
Sure.
sir.
Sure. I'm trying to get back to the workspace where I had the Zoom meeting, but I'm not able to.
Sir, stop
do that.
screen. Stop share. Stop
I'll
share.
stop sharing. Just one second. This is an old computer. It takes time to respond. Okay, I stopped sharing. Oh, yes, I stopped sharing.
Yes.
I guess I'm back here. Okay, good.
I just want to confirm participant can unmute themselves, or is it open? Can anybody from physics faculty try this? Unmute and say something. I hope they can unmute. Yes. Students, any student can tell whether they are able to unmute themselves?
Hello, sir.
Yeah.
Yes, sir.
Yes,
Good,
yes,
good,
sir.
good. Okay, now it's good.
Yes. If you have any questions, you can directly unmute and please ask.
I thought someone was asking.
Yeah, I cannot hear, sir. Sorry, I'm not able to.
I thought some student wanted to ask.
You can raise your hand also, student, if they want.
May I interject? I've sent you the PDF file of my slides, the rest of it which I couldn't show. So please feel free to share it with any students who might be interested or others who might be interested.
Yes, sir. We will share.
As I said, the full article is in resonance in April last year. So
That I will also share, sir. I know that.
So in the meantime, Professor Bal Krishnan, may I ask
Sure,
one
absolutely.
question while we wait for
Sure.
some students? In quantum mechanics, we have this hydrogen atom, which is the analog of the Kepler problem. And we know that the SO4 symmetry is responsible to explain the degeneracy of the wave functions there. So are there quantum analogs in higher dimensions?
Yeah. Yes.
And what are those?
Yeah. So it's a very good question. The automatic thing to do would be to quantize this system and ask, can the Kepler problem be quantized in n dimensions? And the answer
yes.
The answer is yes, one can do so. The Casimir invariants I wrote down would correspond to quantum numbers in that case.
Sure.
And one interesting thing that happens is that the square of the total angular momentum, whose eigenvalues are little l times little l plus 1 times h cross squared in 3 dimensions, that formula gets changed in n dimensions. And it's not L times L plus 1, but L times L plus n minus 2.
Okay.
So
all
if
right.
B is 3, then that's the eigenvalue of the square of the angular momentum, which you define as the quadratic sum of Lij squared half, etc. So that there are small changes of that kind, and the dimension dependence comes out explicitly in these cases, as you can see. The other quantum numbers would correspond to the other Casimir eigenvalues of the other Casimir operators, as you expect in this case. So once again, you're absolutely right. The maximal superintegrability here leads to accidental degeneracy in quantum mechanics.
Okay.
And as you pointed out, in 3 dimensions, the symmetry group of the Hamilton, this is a very important statement that Professor Deshmukh has made, that the Hamiltonian is invariant under the rotation group in 3 dimensions in the normal case, SO3. But the problem itself, the dynamical symmetry group of this Hamiltonian, is a larger group which happens to be SO4 in the case of bound orbits, and SO3, 1 in the case of hyperbolic orbits or open orbits. It becomes the special relativity group, Lorentz group, for open orbits for E greater than 0, and the Euclidean group in 3 dimensions for E equal to 0, the parabolic orbit. In n dimensions, the symmetry group becomes SON plus 1. And it becomes SON, 1 for hyperbolic orbits, and a corresponding Euclidean group for the parabolic orbits for E equal to 0. So no surprises, except that the counting of the angular momentum components, etc., is a very interesting exercise in combinatorics. It shows how delicately balanced the Kepler problem is.
Yes.
A little bit of perturbation, as you know very well, of the 1 over R, and you have spin orbit coupling or something, and the degeneracy is lifted immediately.
Yes.
But interestingly enough, whole families of potentials have been found where you can actually arbitrarily strong perturbations can be applied in this family, and the symmetry remains. So in that very specific sense, it's fairly robust, but in general, a non-spherically symmetrical perturbation will knock you out. Or even a potential which is spherically symmetric, but not a 1 over R power, but admixture of something else.
I think there is a question from a student. Arvind, can you read it out?
Yes, sir. Sir, the question is, question is from Monica. Monicana. And the question is, I came across killing form that helps to simplify the Lie algebra. If you could give some insight into this.
I'd have to define what killing vectors are and what vector fields are to start with and so on. But you're quite right. A systematic way to actually approach this is not an answer directly to your question, but it's related. A systematic way to quantize in, for instance, curved spaces, when you have a space with curvature, intrinsic curvature, and you want to do quantum mechanics in this space, what sort of formalism would you apply? How would you write it down, etc., etc.? What are the rules of quantization? You need these killing vectors and killing forms and so on. So this is really a topic in differential geometry and calculus on manifolds. It's a technical topic. I don't want to get into the details here, but it's a very basic issue here. In fact, if I may go off on a tangent here, it would be a very good idea today in the 21st century, in the year 2021, it would be a very good idea to include in the M.Sc mathematical physics courses, especially the advanced courses, the elements of differential geometry. What's meant by intrinsic curvature, what's meant by manifold, what's a unifying feature, what's a symplectic manifold, etc. This would be a very useful thing to add in terms of physical applications. One of them would be quantization on spherical surface, on curved spaces, for instance. If you want to do quantum mechanics of a particle which is constrained to move on the surface of a sphere in 3 dimensions, you could regard it as a particle moving in a space of intrinsic curvature, intrinsic Gaussian curvature, and then what happens to the del squared operator? It becomes the Laplace-Beltrami operator, etc. And what are the rules of quantization? How would you write it down? That depends on using killing vectors.
Sir, is there any possibility to construct such family of potentials mathematically, or no such possibility, like one R and one? Like,
yeah, we can classify such potentials. We know what's necessary. It's very hard, though, to given an arbitrary function Hamiltonian, to find out what the dynamical symmetry group of this Hamiltonian is. So that's a good question. How do you find this dynamical symmetry group? For the Kepler problem, it's because Laplace already knew about the Laplace-Runge lens vector, and we followed in his footsteps and do this. How would you start? By identifying, given a Hamiltonian, how would you identify this quantity? It's not easy. What is being asked, however, is the Hamiltonian analog of Noether's theorem here, which is well known in Lagrangian mechanics. But in Hamiltonian mechanics, the analog of Noether's theorem is slightly different. It places a role on symmetry, and it says that those constants of the motion, in other words, those functions which are independent of the Hamiltonian and Poisson commute with it, which also generate canonical transformations, are the generators of the dynamical symmetry group of the system. So to identify the generators of the dynamical symmetry group, you must find those constants of the motion which also generate canonical transformations. Or another way of putting it, a better way of putting it is, those generators of canonical transformations which happen to be constants of the motion are the generators of the Lie algebra representing the dynamical symmetry group of the system. So I actually had in these transparencies the algebra obeyed by the angular momentum components together with the components of the Laplace-Runge lens vector. That algebra has got to be identified, and that's what tells you what the Lie group, the algebra is, and then therefore the Lie group itself.
Sir, I have one question. Sir, in recently in quantum many-body systems, if we have some toy model kind of, if some solvable models exist, and then from the understanding of that solvable model, we try to perturb the system and make it unsolvable, and then trying to study this chaotic systems.
Yeah.
So now we have the completely integrable system in classical higher dimension. Can we somehow make it non-integrable so that it will make us to study the chaos in higher dimension in classical systems?
Yeah, sure. Yeah, that's a good point. Certainly it can be done. As you know, the problem with Hamiltonian dynamics is that either you have fully integrable Hamiltonian in the Liable-Arnold sense, or you have chaos immediately. There is for at least some initial conditions. So as the invariant tori keep getting destroyed more and more and the perturbation increases, things go from completely integrable to completely chaotic, maximally chaotic system. But the fact is that as soon as you don't lose complete integrability, full integrability, There is a non-zero set of non-zero set of initial conditions for which the motion is guaranteed to be chaotic. So you'll have some Lyapunov exponents at least immediately present. And as you know, the homoclinic tangle takes over, and that's what is responsible for Hamiltonian chaos. Unlike dissipative chaos, which has many mechanisms, Hamiltonian chaos, we know only one mechanism. That's through the homoclinic tangle. And that, as you know, is a tangle immediately. Yet another way of saying this related to it is the fact that as far as chaos is concerned, the moment you have, you must have at least three variables, three-dimensional phase space, so to speak, with nonlinearity and so on for exponential sensitivity and so on. But we have no quote-unquote integrable models in the case of differential flows, in the case of continuous flows in time. In the case of discrete maps, we have fully chaotic maps which are quote-unquote solvable in the sense that I can write down the nth iterate in terms of the first iterate explicitly, and it will show exponential sensitivity and so on, like the Bernoulli shift or the tent map or any of these solvable maps. There's no such analog in the case of differential equations because the solution is just not computable. It's just not integrable. That's it. It's solvable in the sense of you can rectify the equations of motion and write down the solutions numerically. Given a time step, you can go from one time step to another and integrate it. But it's not integrability. So this is the difficulty. On the other hand, these models, as you point out, they act like the hydrogen atom. They are the sort of solvable models from which you can now branch out and look for perturbations which will take you out and so on. And there are things like the CAM theorem and its extensions and its variations and so on, variants, which would help to some extent. So apart from the fact that the moment you go to higher dimensions, the phase space dimensionality, numerics becomes much harder because of the dimensionality. Aside from that, in principle, yes, one can use solvable Hamiltonians in such cases.
Thank you, sir. If no more questions, let me move to vote of thanks. I thank Professor Bal Krishnan for accepting and giving a wonderful talk in this occasion. And I'd like to thank Professor, our beloved director, Professor K.N. Satyanarayana, for addressing the program and all his help and guidance. I would also like to thank Professor P.C. Deshmukh for very nicely introducing and wonderfully introducing Professor Bal Krishnan. And I thank our departmental HOD and all the faculty members for supporting this program. And also I thank all the M.Sc students and other students who have joined this program. Thank you very much. Thank you.
May I add my best wishes to the students for a wonderful career.
Thank
and
you.
to all of you, and to all of you at the start of your careers. So I wish you all the very best for this endeavor. And I do look forward to be able to someday visiting in person when the situation improves.
It will be a great pleasure, sir.
And I really love to do that. And as Professor Deshmukh said, it would be nice to have some semblance of normalcy so that we can all get together once again and meet in person.
Geographically, you are nearby, so that may reduce some complication.
Well, last year or maybe the year before last, I don't remember now, I gave part of a course on non-equilibrium statistical mechanics at ISER, Tirupati. Professor Ambika organized it. And Professor Rajaram Nityananda and I shared the course, and we were supposed to visit Tirupati at least 2 days a week and do this. And we couldn't do it, and then all this havoc started. I mean, chaos started, and then of course everything fell apart. But I hope that there is an occasion in future when we can do this.
Hopefully, and soon, sir.
So, well, this online is not the ideal situation, but it's at least something better than nothing. And I think people are getting used to it. Certainly, old people like myself find it much harder to get used to, but I think the young faculty has taken to it quite easy.
But today's program was very smooth, sir. We were able to clearly hear you.
Well, I'm thanking my lucky stars that the power didn't go off, because this computer is not on this supply to this computer is not on an inverter, and the computer's battery has died. It's an old, so it's actually plugged in directly into the wall socket. I didn't want to say that in the beginning, but now that the event is over, I'm glad that it went off without a hitch. And well, technology, I must say, has made many things possible, because Professor Deshmukh is in Bangalore and I'm in Chennai, and you're in Tirupati, and so on. It's remarkable that it's almost like across in a room.
It is, yes.
Talk. It's really remarkable.
Before we end this session, I would also like to say, although Teachers' Day was yesterday, but we all young colleagues learn a lot from your NPTEL lectures, your books.
Thank you.
And the students also fond of your lectures. So we wish you very happy Teachers' Day, sir.
Thank you very much. Thank you.
And please continue to give us, interact with us, and we will also seek your help.
Yeah, sure.
Wherever possible. And I know you are many of the times you're not available with the time, but wherever possible, sir, please give some time to us. It will be great. You're a young department, and your interactions, your motivation, your guidance will certainly be very helpful to us.
Yeah. I must say that when ISET Tirupati started and Professor Satyanarayana was going there to take over, etc., many of us felt very reassured that Pranav and P.S. Natarajan are going to be in charge of setting up the place and guiding it through a very difficult initial days and initial years. And so Professor Deshmukh has, of course, been tireless in this effort. I ought to mention here that in this problem of dynamical symmetry, there's a very nice article by Pranav Deshmukh and Jim Libby, also in resonance. And Pranav, I believe it was a couple of issues before the central force problem that we wrote.
Yeah,
it was
yeah.
We have a reference to it somewhere, but
it was around the same time, just before your article.
Yeah.
Sir, in 2020 of your article, this article, it is referred also, Deshmukh sir's article.
Yeah.
Yes, exactly. Yeah, referred to it because it was also in resonance.
Yes.
And it was just a little bit earlier. So it was a nice statement of it. I was looking around for a very appropriate reference to an article on dynamical symmetry. And there are many available in the literature, but we wanted something that would be accessible to students at the right level and very appropriate. And we know that I knew that this article had been published. So,
our director, sir, is also with us, sir.
So may I ask, how many students have joined the M.Sc program?
Sir, last we have 15 vacancies, sir. We started with 15 number of students. So last year, all seats were filled. This year, we got 14 students. So all along, we have 29 students. Along with that, we have PhD students also. Almost all of us have, on average, 2 PhD students, which means we have almost near to 15 students. Then we have some 2-3 project students also. So it's a good size of department. As sir mentioned, we will be soon joining with some more faculty, 5 faculty. Arvinda has already joined, which means the department will be soon bigger. And
have the permanent premises been built as the
I'll let the director sir answer this.
Yeah. So what we did is, very quickly we built some hostels and labs and classrooms. So from 2018, students have been living in the permanent campus.
Hostels. Oh, I see. Okay.
Yeah. Within the first 3 years, we managed to